Greetings, Earthlings. Today I want to talk about what I'm calling the Nova 445 computer. Why is it called the Nova 445? Well, we'll get into that, I suppose. We'll start with a list of requirements that I came up with. And the first one is that it will emulate a Data General Nova computer. And of course, what I mean by emulate in this respect is that it can run existing software for the Nova, not simply that it implements the Nova instruction set. And that has implications for the architecture. For instance, it means that the I/O has to be implemented using Data General's I/O subsystem rather than memory mapped I/O, and things along those lines. Okay, so that's number one. Number two is it will use the Fairchild F9445 microprocessor. There it is, right there. Okay, I have two of them that I've managed to acquire, and so I'm going to make use of at least one of them and have one as a spare. So put those two together. Nova, well, of course, this implements the Nova instruction set, but emulates the Nova, uses the 9445 I came up with, Nova 445 for the name. What's a Nova? Well, that was a range of mini computers made by Data General Corporation. Original one was released in 1969, I believe. And it's a 16-bit machine. And as I sort of mentioned previously, it has a separate I/O subsystem. It does not use memory-mapped I/O. This is an original instruction reference card from that era. Yes, I have used these Novas in the past. And what's a Fairchild 9445? Well, that's a microprocessor that Fairchild came out with in, I think early 80s. They originally came out with something called the 9440, which was their first shot at emulating the Nova instruction set. And so the 9445 is a second generation of that processor. It's based on I3L technology. What's the extra I? Let's see. It's integrated injection logic is I2L, and they added another I, which is isoplanar. So that was their implementation of I2L. I2L was at one point, I guess, intended or hoped to be, the next generation of super fast computing or whatever. Its competition was CMOS, and obviously CMOS won out in that. Okay, so back to requirements. We've seen that's how we got here. Since it's going to emulate a Nova, I should use my pointer. Well, that's hard because, okay. I want to have provision at least for a blinking lights and, toggle switches front panel. It's not a requirement that be used, but I want to allow for it in any case. So it can have the sort of look and feel of a Nova if I want it to. But I also want to include a provision for a ROM-based monitor program and potentially debugger and dump whatever. So, sort of a more modern system rather than just having a front panel. So I want to be able to have one or the other or both. I want it to be capable of running Data General's real-time disk operating system. Whoops, and I left out disk in that description. That was an operating system. And this is an original manual from the day. And there's the RDOS command line interpreter manual. Data General's operating system, well, Data General had a range of operating systems that ran on the Nova line, from DOS, which was single tasking, to there was an SOS, standalone operating system. There was an RTOS, which was, I think, basically RDOS, but without disk support, and then RDOS, which had disk support, multitasking, real-time, obviously, preemptive scheduling, and a bunch of other kind of neat features, supported overlays. So back in the day, before there was, virtual memory and stuff like that, you did manual virtual memory by implementing what they called overlays. That supports all that. Okay, so I want to run RDOS, and then so that leads to a couple of other requirements. In order to run RDOS, I really want to have the full 32K words or 64K bytes, which is the address space of this thing, available when I'm running RDOS. That means that the ROM that had the monitor in it gets mapped out of the address space so that it can run, so that it has the full address space available to it. Because RDOS is fairly large, has a fairly large footprint, even with the overlays. And then if you load up something like Extended Basic, which Data General also had available, that takes up a good chunk of memory, even with overlays. And so then your available program space for a basic program in this example is kind of small, and that's even if you have the full 32K words. If you had, say, 8K words of ROM always dedicated to the monitor so that it was always there, always mapped in, then you only have 24K words available for the loaded code, and that would be a rather severe limitation. So I made that a requirement. Okay, and because we're wanting to run RDOS, there's a minimum set of peripherals that need to be supported. A terminal, serial terminal, RS-232, ASCII terminal, a real-time clock. Now, what we think of today as a real-time clock keeps track of the date and time and so on. What they called a real-time clock was just a crystal-controlled oscillator that could interrupt at different rates. I think it was 1/10 of a second, 100th of a second, 1,000th of a second, or 50 or 60 hertz. And then the system itself, RDOS, would keep track of the actual time based on those interrupts, but it also used it for task switching. A disk subsystem. Now, I'm not going to try to track down an old Winchester disk drive or anything like that and use that. This will be emulated, and actually my preferred medium at this point is MRAM, so it'll be wicked fast. So I'm envisioning what might have been with this system, not trying to recreate, an exact replica of something that existed back in the day. Oh, and along those lines, I don't have a specific cutoff date for chips. I'm using socketed chips everywhere. We'll get to that. That's a board, yeah. There's several reasons for that. One is that it makes replacing them easy if one of them fails. Two, I can borrow the chips for another project if I want to. Some of these chips are really getting very difficult to find. And so if I wanted to use one in another project, I could borrow it by taking it out. And third is that I'll probably end up doing a couple of revisions of the PC board. And again, because the chips are kind of hard to find, some of them, I don't want them soldered in and have to desolder them and potentially destroy them in the process. I want to be able just to remove them and swap them over to the new revision of the board. And then while I was at it, because of some of the chips I used, I just added a requirement, including a provision for a graphics display. Minimum 256 by 256 pixels. And so this is the first rev of the PC board for the CPU and RAM. CPU is going to go there. These are the RAM chips. So you'll see they're not through-hole. I used PLCCs. And these are actually dual-ported RAM. So for the main RAM, main memory of the processor, which will be 32K words by 16 bits, 64K bytes total, these are IDT 7007s, which are 32K by 8 dual-ported RAM. And so I have 2 of those, so I better not destroy one of those. For the monitor, I have space here for some EEPROM, although it could be EEPROM as well, because they're pin compatible. And then one socket here for this is 8K by 16, IDT 7025. Okay, those have 2001 date codes. These have 1998 date codes. These have, let's see, the processors. I have one with an 86 and one with an 88 date code. So like I said, date codes don't matter to me for this. But by using the dual-ported RAM here as well, the other nice thing about these RAMs, by the way, is they're wicked fast. These are like it's 25 nanoseconds. And this one, 25. Okay. So I don't need any wait states when I'm accessing RAM. But since I had these dual-ported RAMs, the IDT 7025s, I said, well, I'll just put that in there. And then, so the other port, I can use, I can hook up a graphics display to it. So as requirements go, that was driven by the available hardware rather than any kind of, marketing requirement or anything. Let's see. So we can look at the architecture here that I've come up with. I've got my processor, which can connect to a front panel. Oh, yeah, okay. So here's the front panel port right here. I/O bus and DMA bus. Oh, okay. So let me back up. By using dual-ported RAM, I allow direct memory access by using that dual-ported RAM rather than using what Data General called the data channel, which the Fairchild chip actually implements, but the data channel steals bus cycles. It's a bus sharing system. So that basically the processor is paused when you're reading a sector off of disk. This will allow that to go on in parallel, as it will only have to pause or delay the processor if there's a conflict. That is, if you're reading and writing the same memory location. So again, going for wicked fast there. Okay, so CPU, provision for front panel, and then I have my monitor, RAM and ROM, and I'll get into that with the dual-ported RAM and the potential for a graphics display out here, which directly accesses on the other port of this RAM. Here's the main processor RAM, 32K words. The disk can access that directly, and the disk is the only DMA device that I have in this system. So that kind of keeps that simple. Here's our I/O decoding because this has I/O instructions, and there's our real-time clock and our terminal. Now I did allow on the board for additional devices, which I called Dev A, B, C, and D. However, and by the way, the I/O decoding is on this board, but this is not the I/O board. The I/O board is a separate board, which will stack on top of this one, or under it probably. So you can look at this board and say, well, it could be more dense, but when you see the I/O board, and I haven't finished laying out the I/O board, but when you see the I/O board, it's quite a bit denser. So part of the reason that this is as large as it is to allow more space for that I/O board, because I'm not even sure right now that I'm going to be able to fit everything I want onto that board. Okay, back to this. Okay, real-time clock and TTY. Okay, so talking about this monitor RAM. The CPU really has 15-bit address space, and everything is word addressed. At least the Nova does. The Fairchild chip has a 64K mode where it can access 64K words of memory. But at startup, it's in pure emulation mode, pure Nova mode, so it's 32K words. So on processor reset, the monitor memory will be mapped into the processor's address space, and the main memory will be disabled. So that will allow you to, that would allow you to toggle in a program up to 8K, and such, into the monitor RAM. If you're not using the graphics display, which is probably going to use a large chunk of that RAM, and you might get weird output on that if you put a program in there. But anyway, that's neither here nor there. But then the program in RAM. So on reset, it will execute the instruction at the highest memory address. So the ROM will be mapped into the high memory space, and we'll be able to run our monitor program. But then what I've done is that when we put it into 64K mode, then this memory will get mapped into the high 32K, and this memory will be mapped into the low 32K. At that point, we can convert back, set the processor back to 32K mode, and only this memory is accessible. Okay, so we can start up in this memory, in the ROM code, have a monitor program, and the monitor can have a command that says boot from disk. Okay, well, the first thing the monitor will do is, in that case, is probably set the processor to 64K mode and to make this memory available. And then this code, the code that's in here, will know that it's running in 64K mode, and so it will be written accordingly. It can then have a command that says boot from disk, and what that will do is set it back to 32K mode and tell the disk to load the code. And the disk boot just loads from sector 0 of the disk into location 0 of memory, and up to 16 sectors, a sector being 256 words? I forget, or 512 words. The disk sector. The particular disk drive that I'm emulating if you want to go look this up, is the 4047. It's the disk cartridge drive, what was commonly called the Winchester drives back in the day, although I don't think that's really an accurate description. We called them Winchester drives. Right, so that's the overview. And as noted, I have a first shot at the processor, RAM, and I/O decode board done. So I will start playing with that and debugging that. And meanwhile, I'm continuing on the design of the I/O board, which has those 3 peripherals: terminal I/O, real-time clock, and the disk emulator. And of course, the terminal I/O and real-time clock I've got designed and actually laid out. And so I have about that much space on the board for the disk emulator. So it's the way the board is currently laid out. Real-time clock is here. There's some interrupt handling chips down here. The TTY is up here, and that's how much space I have for my disk emulator. So we'll see if I can make it fit or if I have to play some other games with that. Go to a third layer or, in some way move some things off of that board. But initially, I've got enough to keep me busy. With this, I've got to test it, which means creating a minimal front panel, at least. The absolute minimum front panel is just to do a reset, which I could do and hang the logic analyzer on this and see that it actually does access the right memory location stuff, see if those chips are any good. The second level would implement a reset, a self-test, a stop, and a continue. And then the third level is a full switches and lights front panel. Now, speaking of self-test, I know it's there, but it's not well documented what it actually does. So if anybody has any clue what the processor self-test on this Fairchild chip does, how it operates, and what I would expect to see to tell me that, yes, it's operating correctly or no, it failed, let me know. Because, I'll play with it, and I'll put the logic analyzer on it and see what it does. But I haven't found any documentation on what that self-test actually does.